Hello and welcome back, people. So we've gone ahead and in chapter 25, we've understood how to store electrical energy in capacitors. But a capacitor is a very static way of storing electrical energy. In this chapter and in the next chapter, we're actually going to understand how charges can be made to move around in circuits and actually do useful things for us. So this chapter is going to introduce us to notions of current, resistance, and electromotive force. So let's go ahead and dive in. Now, our notion of current is typically the one that our pedestrian notion of current is typically the one where electric current is carried in wires. And this pertains to the fact that electric charges are flowing through that wire and doing something useful for us in terms of doing useful work. So one concept that we're going to understand is the notion of currents, and we're going to understand the notion of currents in a somewhat more sophisticated way than we have studied so far, so that we understand how current flow takes place on a microscopic basis. The next thing that we're going to understand is a new circuit element that we're introducing in our study called the resistor. A resistor, as the name suggests, is something that in fact resists the flow of current inside the device. But in doing so, we can actually go ahead and get some useful work out of the resistor. So um, uh, the notion of a resistor, the verbiage of a resistor doesn't fully do justice to what it actually does for us. Now, with that said, we also want to understand how electricity can be transferred from one location to the other. And that is actually what we're going to understand, namely that anytime you have electrical energy being transferred from one location to the other, you can actually do work. And this notion of electrical transmission is also something that we're going to study in the course of this chapter. Now, why is electrical transmission useful? The answer is that if you think about the energy that is generated in the electric energy that is generated in the United States, a certain fraction of it, a certain completely non-trivial fraction of it, is actually lost in the transmission lines over which this electric energy is transmitted from the power station to, in fact, your homes. And therefore, it behooves us, if we want to understand the notions of green energy, to actually understand how electric energy is transmitted from one location to the other and what the losses could possibly be. So with this, let's go ahead and dive into the first section of this chapter, which deals with the idea of current. Now, anytime you have electric charges flowing through some region of space, you can actually go ahead and develop the concept of a current. So you can actually say that you're measuring, in fact, the number of coulombs of charge flowing per unit second. And we can actually go ahead and have a notion of um, and we can define a special unit for that concept, which is an ampere. So an ampere, in fact, measures the number of coulombs of charge flowing through a device or a wire in 1 second. Now, charge needn't be just flowing through wires. The reality is that you could even have charge flowing through space. For example, if you have a charged up Van de Graaff generator, then over time it will lose its charge. And the reason it loses its charge is that, in fact, charge is flowing through the air and actually flowing back to the ground, thereby causing the Van de Graaff generator to lose its charge. And of course, such charge loss is not does set up a current flow, but it doesn't produce current flow in a wire. Now, just to kind of set up a baseline, just to kind of explain things to you, a typical household in the United States draws about 20 amps of electricity. So if you go ahead and go to the basement of your house and you see the fuse box, most of those fuse boxes, depending on the size of house that you have, will either be rated for 20 amps, or if you have a particularly large house, then it might be rated for 40 amps. So with this understanding, we can now go ahead and develop a more microscopic understanding of current flow. So imagine if you like that we have a wire, and imagine if you like that we have positive charge carriers, then we can go ahead and measure the number of charges that actually flow through some imaginary cross-sectional area of this wire. And therefore, we can say that we have delta Q amounts of charge flowing through the wire or flowing through that cross-section in an amount of time delta T. So this allows us to set up a notional definition of current flow. And in the next transparency, we'll actually go ahead and use calculus to firm up this notion. Now, with this said, I've often mentioned to you all that in a metal, you typically have negative charge carriers, namely the electrons are the guys who actually carry the current. So you can imagine an analogous situation to the one shown above, namely you can imagine a wire out here. So this is a wire. And in this wire, you can imagine that you have negative charge carriers like so. And these charge carriers could be moving to the left. So in the picture above, you have charge carriers that are moving to, you have positive charge carriers that are moving to the right. In the picture below, you have negative charge carriers that are moving to the left. Now, I want you to realize that having positive charge carriers that are moving to the right gives you a notion, the conventional notion of a current flow that is taking place to the right, and we denote this current by a capital I. But you could actually have an entirely analogous situation where, because you have negative charges moving to the left, you could actually go ahead and say that you have an entirely equivalent current flow I going to the right. So in many different types of situations, imagining that you have positive charges moving in a wire going in one direction is in fact entirely equivalent to imagining that you have negative charges in the wire that are actually moving or drifting in the opposite direction. Now, why did we come up with this notion of positive charges? The answer is that the notion of electrons and nuclei was only set up in the early part of the 1900s, whereas people knew about charge and current even in the 1800s. So they set up this notion of charge carriers and charge flowing through wires even before they knew exactly what it was that was carrying the charge in most typical circumstances. So with this, we can actually go ahead and understand that for most workaday situations, it's not going to matter if you think about positive charge carriers flowing in the direction of current flow, and that would be completely equivalent to having negative charge carriers actually carrying negative charge in a direction that is opposite to the indicated direction of current flow. However, I will caution you all that there are certain effects that we will actually study later on, namely the Hall effect, which in fact allows you to distinguish between the fact that there's positive charge carriers or negative charge carriers in a particular piece of wire. So this is an important idea. And let's go ahead and in this next transparency, we're just going to firm up our understanding of current by saying that we can actually go ahead and use calculus to go to the limit, and that allows us to say that the best definition of current is to actually write it as dq by dt. So with this, let's go ahead and reaffirm that in various materials, you could in fact have positive or negative charge carriers. It just turns out that in typical metals, the charge carriers happen to be negative. But in semiconductors, you could as well have positive charge carriers and negative charge carriers. And it doesn't matter what you have, your notion of current will come out the same. So in a typical ordinary conductor, which might actually be made up of metal, you could actually say that the direction of current flow is opposite to the direction of the flow of electrons. Okay? So with this, we come up with the notion of charge carrier as something that moves through an object and carries current. So with that, we will also recognize that The convention, though, especially because it came before we understood the notion of electrons and protons, is to actually go ahead and imagine that you have positive charge carriers that are carrying current in the direction of the current flow. So with that, let's now go ahead and nevertheless use our more sophisticated understanding of microphysics to develop a microphysical view of current flow. So imagine, if you like, that you have a conductor, and this any typical conductor will have a certain number density of charge carriers. For example, copper is a particularly nice conductor, a particularly good conductor, and you can actually say that copper has a larger number density of charge carriers. It's a uh, much more effective conductor. Copper is a much more effective conductor than, say, iron, and that is mainly because copper has a larger number of charges per unit volume. So we have this notion of a number density of charges, and this number density of charges is fixed for particular materials. So for example, for copper, you have a certain number density of charges. For iron, you have a different number density of charge carriers. And for other objects, for gold, you might have a different number density of charge carriers. And so the concept of number density of charge carriers basically refers to the fact that N has units of number of charge carriers per meter cubed. Now let's go ahead and take a wire with a cross-sectional area A, and let's consider a length delta x of that wire. Therefore, how many charges will we have in this volume? The answer is that the number of charges is just equal to the number density, which has units of number per meter cubed, times a volume which has units of meter cubed. So we'll actually go ahead and say that number density multiplied by A multiplied by delta x gives us the number of charges in that particular section that we've identified out here. Okay? So with this, we can ask how much charge is carried by that in that object, and it actually turns out that the charge of each charge carrier is also fixed. So for a particular choice of material, the charge of the charge carrier is fixed, the number density of the charge carriers in that material is fixed, and so N is fixed for a particular choice of material, Q is fixed for a particular choice of material, and we just go ahead and take the total number of charges that we identified, which was N times A times delta x, and we actually go ahead and multiply it by the amount of charge per each charge carrier to find the total amount of charge in that particular volume that we have identified. Now notice that if I have an electric field that is applied to this conductor, or it could actually be a semiconductor, then this electric field will induce a certain amount of drift velocity inside the charges, inside the free charges that are moving in that conductor. So we'll actually go ahead and say that there's a certain amount of proportionality between the electric field in a conductor or in a semiconductor and the actual speed with which the charge carriers are moving through that conductor. Okay? So with this, and we'll actually go ahead and make this concept very concrete in the next few transparencies. But let's go ahead and say that there is a certain relationship, and therefore we can actually go ahead and say that for a particular impressed or applied electric field, you will actually have a particular drift velocity for the charge carriers in this conductor or semiconductor, and that actually allows us to say that delta x is actually equal to the drift velocity v sub d times delta t. This allows us to write delta q as being equal to the number density times the cross-sectional area times the drift velocity times delta x times q times delta x. But delta x, okay, I'm sorry, let me just back up a little bit. Okay, so let's go ahead and discuss this formula all over again. So we can actually go ahead and say that delta q is just equal to the number density times the cross-sectional area times the charge of each of the charge carriers times delta x. But I've related delta x to the drift velocity and the amount of time it takes for those charge carriers to go through this cross-sectional area. Therefore, I will actually go ahead and replace delta x with v sub d, the drift velocity, times delta t. This actually allows me to go ahead and write delta q divided by delta t. And using the previous formula, I can write it as n times q times v sub d times a. Okay? So now we actually understand that delta q over delta t is just our notion of current, and so we've related the current to something microscopic, namely the number density of charge carriers, the charge of each of those charge carriers, the drift velocity that is induced in that conductor due to the presence of the electric field, and the cross-sectional area. So with this understanding of current, with this microscopic understanding of current, we're now ready to go ahead and understand at a more intuitive level how how the drift velocity is actually related to the impressed electric field in a conductor, or actually in a semiconductor. So imagine, if you like, that I have a negative charge carrier out here, and on this region, within this region of metal, I actually go ahead and put an electric field that is oriented to the left. Okay, this electric field will actually apply a rightward force to the electrons that I'm considering. So imagine, to begin with, that this electric field is not present. What will this electron want to do? Because it has a certain amount of thermal energy, it will actually be rattling around or moving around with a certain velocity. However, it will not go far. It will not go far because it will actually go ahead and impact with some other atomic nucleus out here. And when it impacts with that atomic nucleus, it will be totally scattered. Namely, it will go off in some other random direction and travel along another straight line. And it will not go far again because it's going to go ahead and bump into another nucleus out here. And then it's going to go ahead and have another scattering, which will take it, for example, out here. And at that location, it will bump into another nucleus yet, which will go ahead and send it off in another direction. And most likely, after enough of this rattling around, it's actually going to go ahead and come back to a location that is quite similar to its original location. So unless there's an external applied electric field, this electron is not going to move very far from its original location, even though it is moving at a very high speed, and even though it is going ahead and having a great number of collisions with the atomic nuclei. Now imagine, if you like, that I switch on an external electric field that is leftward oriented in this metal. Then what will happen is that because the electron is negatively charged, it will actually feel a net force that is oriented in the rightward direction. So this, if we can replay the same motion of the same electron, but with the electric field turned on, then we realize that this electron is not going to go ahead and move along a straight line. Rather, it will follow a curved path, and it will maybe have a collision with some other nucleus out here. But notice that its path has been shifted a little rightwards because of the presence of the electric field, which gives it a rightward force. Then it might actually go ahead and have a scattering and move somewhere out here. So notice that it didn't move as much to the left, but rather it moved a little bit curvaceously to the right, and therefore it will have another collision with some electron out here, with some nucleus out here, and then it will actually have another scattering, and it might actually move a little bit in this direction. Let's say it moves here, and then it will have another scattering yet with some other nucleus, and then it might actually go ahead and have another movement to some other location out here, and it might actually find itself in this location at the end. So we see that the same electron, if we could run its motion once without the presence of the electric field, will not go far from its original location. The same electron, if we switch on an electric field, will still continue to have a copious number of collisions with the nuclei. However, on average, it will start moving in the rightward direction if the original electric field is in the leftward direction. This is exactly what is shown to you in the above picture also, where each of those zigzags in the motion of the electron indicates a collision that it has out here, out here, out here, out here, here, and here. I'm sorry. Okay, so now that we understand why a drift velocity arises, we understand that if we have an even larger electric field, then this electron is going to have even larger force in the rightward direction, and therefore we will have an even larger drift velocity. So we understand that there's a connection between the electric field that is externally impressed or imparted and the drift velocity that the electron acquires. The larger the external electric field, the larger the drift velocity of the electrons. So with this, we understand that even though there's there are a copious number of collisions, we can actually have the charge carriers move with a certain drift velocity, and these forces basically cause the electron to move in a wire, and if you have a net number of all the electrons drifting in one direction, you can actually have a substantial amount of current flow. Now, just to clear up a misconception, the electrons are already present inside the wire. The electrons were not provided by the battery. However, what the battery, if you connect the ends of the wire to a battery in order to obtain a voltage difference and thereby an electric field in the wire, then what the battery actually does is it actually supplies an external electric field, and the presence of the electric field therefore produces a drift velocity inside the wire. So the battery is not a supplier of electrons, but the battery in fact sets up the electric field inside the wire. Now just to get a measure of the numbers out here, if you have a 12 gauge copper wire, which is a rather thick copper wire, and if you're carrying 10 amps amounts of current in that wire, then it actually turns out that the drift velocity of the electrons is amazingly tiny. It's 2.23 times 10 raised to minus 4 meters per second. So you actually realize that the electrons are literally crawling along in the wire. The drift velocity of electrons in a typical wire is amazingly tiny. However, the wire can carry a large amount of current, not because the drift velocity is large, not because the charge on each of those charge carriers is large, but because most typical conductors have just a gigantic, a humongous number of free electrons within them, and that allows them to actually carry significant amounts of current. So with this understanding, we now want to develop a notion of something that is independent of the geometry of the wire itself. So imagine, if you like, that we have two possible wires. The wire to the right is thicker, the wire to the left is thinner. both wires are carrying the same amount of current in them. So we can say that I, the current in the wire, is just equal to the number density of charge carriers times the charge on each of those charge carriers times the drift velocity V sub d times the cross-sectional area A. So notice that in fact the number density is independent of anything else. It's just specifically set for each different material. The charge of the charge carriers is specifically set. The drift velocity we have shown is proportional to the externally impressed electric field, but notice that the area A depends on the geometry of the wire. So we can actually go ahead and divide out by the area A to obtain the current over the cross-sectional area of the wire, and this allows us to obtain something that is independent of the geometry of the wire, and we call this the current density. Okay, so the current density J refers to the amount of current flowing through a cross-sectional area, and the cross-sectional area is measured in meters squared. The current is measured in amps, so the units of current density is in fact amps per meter squared. So with this understanding, we realize that current density J is actually equal to the number density of charge carriers, the charge on each of those charge carriers, times the drift velocity. Now, the interesting thing is that we can actually relate the drift velocity to the externally impressed electric field. So imagine, if you like, that you put a voltage delta V across a wire that has a length delta X. Then you can actually say that the voltage is equal to the electric field times the displacement. Therefore, the voltage delta V is actually equal to the electric field that is produced inside the wire times delta X, which is the length of the wire over which you've applied that voltage. This allows us to relate the voltage applied to a wire to the electric field that is present inside the wire. Now, once we have a measure of the electric field inside the wire, we realize that the drift velocity V sub d is in fact proportional to the electric field itself. Now, this is only true for conductors. It's especially true for conductors. It's not especially true for semiconductors, but we'll see why and how in a subsequent section. So we realize that for the simplest case of conductors, the drift velocity is in fact proportional to the electric field itself, and this allows us to relate, to make a measurement, or to make a proportionality where we say that in fact the current density, which does not depend on the geometry of the material, is actually proportional to the drift velocity, which in turn is proportional to the externally impressed electric field. And this gives us the proportionality constant between the current density and the externally impressed electric field, and that constant of proportionality is known as sigma, and it has the name of conductivity. So notice that conductivity relates to exactly what we think it is. Namely, we say that copper is a better conductor. We say that copper is a better conductor because it has a conductivity that is actually quite high. We say that iron is not as good a conductor. We say it's not as good a conductor as copper because the conductivity of iron is in fact lower than the conductivity of copper. So if you put the same amount of external electric field on copper, it will produce a larger current density because the conductivity of copper is higher. If you put the same amount of electric field on a similar chunk of iron, it will produce a smaller current density, a smaller current density, because the conductivity of iron is in fact smaller than the conductivity of copper. Now, typically, that is exactly why people like to use copper in the wiring that is in your home. Now, in old-fashioned homes, they actually used copper wiring. In modern homes, sometimes they use aluminum wiring, and the interesting thing is that aluminum costs a lot less than copper. So the electrician who volunteers to replace the copper wiring in your old homes is actually doing himself a very nice favor, because he gets to pull out all that highly valuable copper and replace it with aluminum wiring, which is what is typically used these days in lower cost wiring. But the electrician is actually getting something out of that wiring, because the copper costs a lot more on the market than the aluminum. So with this, we actually understand that conductivity is a very useful concept. Now, the metals that have highest conductivity are the noble metals like gold and silver. But you don't use gold and silver in the wiring in your house, of course. But you actually do use a certain amount of gold layering in, for example, the electrical connections that are made in your cell phone. So you might actually see that if you have a firewire that you connect to your cell phone, you might actually see that it's a little gold plated, and that's done basically to establish a good contact between, sorry, and that's actually done to establish a good contact between the cell phone and your firewire. So with that, I'll essentially stop and hope to see you in the